Swayam Prabha. Digital India. Educated India.
Welcome back. Let's start. In the last lecture, we were talking about the nesting forces. So we'll continue from there. So just try to recap. So what we are saying here, that if we put a fourth post, that may not be enough to provide nesting force. So the fourth post is always over constrained, and it does not replace the nesting force. And why? Because again it's still rigid if we consider this case. So in order to provide sufficient nesting force, it should press, and there should be, so these are the contact points. So there should be always some force acting on the post, and that will only happen if it applies some force here. But since it is also a rigid post, and the dimension of the object is also defined, so it's very difficult to get accurate dimensions there. So either it will be too tight, so it will press too much, so there will be interference, or if there is any gap, so there will be no contact. So no contact means there is no nesting force. So it's very important to understand that we cannot use the same kind of contacts to get the nesting force. Another thing to also note down is the way we define the nesting force. What we are saying is along the contact point. So it's always coupled with the contact. So we can always say there is a nesting force, right? This is the nesting force at this contact. Along C2 we have this is the nesting force, what we can say, and C3. But we can always get a single force by combining them vectorially. So that's something we also need to understand, and we'll do some exercises on this, how to find the nesting force. So there are different ways, and without creating problem, what we discussed in the earlier slide, how to get the nesting force. So one is the weight. So because of the weight, we can always get contacts, sufficient contact. So weight can also provide sufficient nesting force, but many times we don't have that luxury. Other is the eccentric cam. So you can see, and if you rotate, yeah, so this is the center, but it's pivoted here. So as we turn, we get the wedging effect, and we can lock it, and again we can get the sufficient nesting force here. Similarly, if we have a spring, so we can use compliant members. So any kind of springs we can use, and we can press it, and we can get the nesting force, and again we can get all the contacts made. So, it is very important to understand that at the contacts we should always have a positive force acting there. Negative means, yeah, there is no contact. So, there is no question of, or there is no question of getting negative values. Yeah, it will be 0 or positive. 0 means we have to find some ways to get the sufficient contact. Another is the screw, we turn and then we can get the force here and then we can get the contacts. So, these are some of the methods. Magnets are also one of them. We can use magnets as well, or vacuum. There are many ways. So, as needed, I think that can be done and we can achieve sufficient nesting force. And it is very important to have that nesting force, then only we can define the exact constraint design or can ensure that we get the desired degree of freedom and constraints. There is a way to calculate the nesting force. What we also need to find is nesting force window. So, there is a window and if any force passing through that area, so in this case is the unshaded area. So, if any force passing through that area, that's a yes. So, it's a feasible solution, and if it's a passing through the shaded region here, what we realize that it's a no. It's not going to give the sufficient nesting force. So, not all the contacts will be made and it will get lifted. So, maybe we will quickly try to see how to find it, how to find the nesting force window in this case. So, for instance, we have this post 1, so contact. So, define the contact C1, post 2 and we have the contact C2 and then post 3, contact C3. So, what we can now define is the constraint lines which is defined along this. So, this is what mentioned nesting force direction constraint because of the 1 along C2. This is because of the contact C2. So, these are the constraint direction. Similarly, if we pass through point C3, so this is because of the contact C3. So, these are the constraint directions. What we also understand that if we take 2 of these contacts, they always create a instantaneous center of rotation. So, we can find ICs. So, for instance, if we take C1 and C2, they are intersecting at this point. So, call it IC 1 2. So, if we are considering contact 1 and 2 only, the object can rotate along IC 1 2. So, if we want to have contact with post 3 or want to make contact C3, the nature of moment, any force if we are applying, any nesting force we are giving, the moment at IC 1 2 should be such that it will try to make positive contact with post 3. So, how is possible? So, one of the ways, so if you apply this clockwise moment at IC 1 2, what we realize that it presses against contact C3. So, this is what is desired. Similarly, if we take C2 and C3 together, the intersection point will be here, and which we can label it is IC23. So, if we try to rotate the object along IC23 and only considering contact C2 and C3, but we realize that it can rotate. But if you want to make contact with C1, so it should push against post 1. So, it means the nature of the moment acting at IC23 should be in this direction, which is again clockwise at IC23. Similarly, if we consider C1 and C3, so the intersection point is here. So, C1 again, so C1 direction is this and C3's direction is this. So, the intersection point will be here and we can call it IC 13 or 31 is the same. So, call it IC 13. So, if we consider only post 1 and 3, the object can rotate along the axis IC 13. So, in order to make contact with C2, what will be the moment required? So, in this case, the rotation, the moment required will be along this direction, which is now counterclockwise. So, any force acting or any external force, nesting force we want to use, we have to understand that all these three conditions should be met together. Then only we should be able to get the sufficient contact or contact with all the three contacts, three poles. And slowly if we start going from these points, what we realize that, so that is why if we go along this line, what you realize is so no, any force coming in this one, it will not comply with IC13 requirement, same with this one. So, this is again, so it is a shaded region, the force should not pass through this area. Similarly, if we start from here IC23 and along these lines, what we realize that if the force passes through, suppose force comes and passes through this line like this. So, because of this line along this way, what is happening is contradicting with IC23 requirement, because it is creating moment which is opposite to what is required. Same with the IC12 also, is a creating moment in the opposite direction, although is fulfilling the requirement for IC13. So, similarly, if we go, we find that this zone, this shaded area is again not valid. So, you can check whether you have this force or coming like this force, these are all not valid solution. But there is one area which is unshaded, and if the force is passing through that one, so for instance, the one is shown here, if the force is like this, what you realize that this force is a good solution. It complies with all the three requirements. So, it gives you all the three moments at the same time. So, it is a valid solution. So, in any force, even this force is also fine. this force is also fine. So, as long as it does not pass through the shaded area, it is a valid solution. So, there are many solutions, and which one to choose, right. So, okay, it gives us a lot of options, but which one is good? So, it depends on what kind of forces we want at the contacts. We may want to have equal forces at all the contacts, or if it is asymmetric and the dynamic forces are such that the sum of the contacts should take more load. So, it depending on our requirement, we can formulate, we can have some optimization also, and we can play with that and we can find the optimum solutions. But we know that as long as the force passes through the unshaded region, it will give us the right solution. So, there is a nesting force window outside which any nesting force will tumble the component and out of the stable nesting position. So, we will not have a stable nested position if the force is passing through the shaded area. So, we can again take up some examples later and try to understand. So, that is about nesting force. So, when we are talking about exact constraint, what we also understand that contact removes 1 degree of freedom and provides one constraint. But what we also realize that a point contact will give rise to a lot of stresses, because the area of contact is very small. So, sometimes we may like to deviate from there, and so therefore, we may go for relatively larger radius, and so that at the contact we can have a fairly larger area of contact, which improves the load carrying capacity and even the stiffness. So, curvature and surface matching, of course, it compromises the exact constraint, but at the same time it improves the load carrying capacity. So, we have to be aware of the consequences wherever we deviate from exact constraint design. What we also observe that the four-legged table is not a stable solution. So, in this case, what we realize, this pedestal has 4 supports, and yes, the exact constraint with the 3 points is valid if it's a rigid frame or rigid object. Here, if it's a rigid and if we have 4 points, we will have a problem and it will always rock, because we are talking about now 4 points. So, it may contact with the 2. So, it will make axis through that, and then it will start rocking. So, which point will be the third one? It depends on the loading, depend on the also the surface. So, yeah, it's a no go. But if we really want to use 4 legs to improve the load sharing and even the stability, and we want that it should be always a stable, it should not rock, then what we have to remember is the elastic deformation. So, we can mitigate over constraint by providing elastic deformation, and in this case, in most of the furnitures, these are large furnitures and they are not rigid, and we can always get a compliance, we can always get this kind of rotational compliance, and because of that, if there is any deviation, so it will come in contact and we will have a 4-point support. But it is happening because we have provided a elastic deformation, or we can say we have provided a internal degrees of freedom in the form of elastic deformation of the table, and in this way it can conform to the surface even though it is not flat, but still all the 4 legs will make contact, but definitely the table will deform. But for most of the application this might be acceptable, but of course if you are trying to design a table for some precision equipments, we may have to find different ways, and it might be possible with the 4 legs, but the deformation may not be on the top of the table, but then we can concentrate somewhere else, and that is something we may learn when we talk about compliant mechanisms or the flexures. So, there are many examples where we have over constraint and we mitigate using elastic deformation. So, for instance, the chairs, they have many contacts. So, in this case we have 5 contacts, but they all have some elasticity here, and because of that it makes contact to the surface even if it is not flat, and we can avoid rocking. The another example is the flange, bolted flange. Again here there are many bolts, and here we consider the elastic deformation of the surfaces. So, when we tighten, the asperity is there, yeah. So, it may not be flat, but then as we tighten the bolts, it will come in contact, deform, and we will get. So, over constraint may not have a problem in that case. What we also rely on in this case is the clearances of the bolts. So, here the main purpose of using bolts is to create that joint, and sometimes we use it to even locate, but as we know that location using bolts may not be a good idea because the clearances are there, and we have to use some kind of jigs and fixturing to get a proper alignment. So, therefore, it is not desired, and we will see some examples where the location and the clamping can be achieved through using exact constraint design. So, we may not have to worry about the proper alignment, it will go to the same location all the time. So, if we create some features on the surfaces, and then we can bolt it and secure the joints. One very good example of this mitigating over constraint with elastic deformation is our wiper blades also. So, as we see here, the glass curvature, and as it swings, so the curvature may change all the time, yeah? But how to make proper contact all the time? So, what you realize that there are many supports here. So, we may want to have all the contacts made all the time irrespective of where you are. So, you are only pressing from here, but how is conforming to the surface, and this curvature may change. So, how is done? So, what you realize that they have a branching, this kind of configuration, and later you realize that these kind of systems are used in many places where you want to conform to the surface. So, there are many point contacts, but still it is not over constrained because you have provided internal degrees of freedom, and that way it self aligns and provide the proper contact or contact force. So, in robotics or in kinematics, Many times we call it under actuated systems, or we can say there are many redundant degrees of freedom. But again, if we talk in terms of machines, is mitigating over constraint with the elastic deformations, and in some of the latest design what you see, it's not the some kind of pin joints, but it's just some hinges, and it can be made with just one piece with the injection molding. So, if we are aware of these methods, I think many times we can replace the expensive items with the monolithic designs, with the plastics, injection molded parts, with proper design, with the hinges, and we can get same kind of performance. This is one case study, and this is a problem in one of the company's printers. And what they have done is they use rigid coupling to connect the motor to the shaft, which is connected to the lead screw to move the bed for scanning or printing. So, moment you connect rigidly, the motor, the lead screw, I think they are all become one part, and this motor is now connected to the frame rigidly, what you see here through these bolts. So, now everything is one part, one rigid unit with no compliance. So, what will happen? Any error, any misalignment in the shafts of the motor and the lead screw will create problem, because there is no compliance provided, and so any deviation, any misalignment, any offset when it starts rotating, although the idea of the motor is to just rotate the shaft without giving any other forces, but since it is rigidly connected, because of the offset and misalignment, there will be huge forces generated, and the company encountered a lot of problems with these units. They try to fix many times, they try to fix the alignment, they try to adjust the bolting, but cannot get rid of the problem. And with the careful analysis, what you realize that it can be easily achieved. So, maybe for some reason they still want to use the rigid coupling. So, this is the axis of rotation. So, you want to provide the torque or motion with the motor. What is required is only the torque or the rotational motion you want, without worrying about the offset and misalignment, right. So, one of the thing you learn is you do not want to, so unless you restrict the motion of the motor in the rotational direction, you cannot provide the sufficient torque. So, you have to constrain it. So, in order to constrain, if you just provide constraint along this line, so suppose if I just look at from this side, so this is the shaft, okay, this may be the motor, so it tries to rotate. So, if I just constrain the frame along this direction, it will provide the sufficient reaction torque, and then the motor should be able to then turn the lead screw. So, one line constraint away from the axis of rotation that can provide you the sufficient reactional moment. And so, in this case what happens, it provides all degrees of freedom, it is not locking other degrees of freedom except this. So, this is a flexure mechanism. So, later we will be learning about this. So, what we call it leaf spring, folded leaf spring. So, for the time being, just remember, if we connect it like this and connect to the other part here, so it can only provide constraint in this direction along the fold line, and which is achieved through this kind of flexure here, and the problem is solved. So, not necessarily we have to use many parts or a lot of tooling or have to do precise adjustments with a lot of jigs and fixtures. Sometimes if you understand the requirement, so requirement is this here in this case, a simple flexures of sheet, folded sheet with a sharp bend will do the job. And of course, yes, the problem has been solved, but at the same time, if we look at the cost part, you have eliminated many components, and so it's a very cost effective solutions. At the same time, the performance is now better, and it will not create any kind of undue stresses on other elements. So, we will take up many examples like this and try to embed these designs in our systems. So, next is load path. Plan the load path in parts, structures and assemblies. So, why we are talking about this? Because whenever we assemble different components to get assemblies, modules, and when we are assembling the moving parts or the units to the structures, the loads, the dynamic loads, the external loads, the loads because of the processes, machining processes, so or the reaction forces, they all get transmitted from one component to another and ultimately to the machine base. How they travel, what is the path they are taking? It is very important to visualize and clearly define, because that is the critical path, and any part along that path, along that load path, that has to be checked for failure and performance. So, it is very important to define the paths of the applied and internal loads also. Internal loads, for instance, the bolting, the temperature, because of the temperature variations, what kind of thermal loads getting generated. I think all those things. So, not only applied, but the internal loads also we have to check how they are moving, what is the path they are taking in the machine, and we also need to visualize through the part or mechanism. Then only we should be able to tell exactly what is going to happen. And the other thing is, are we able to visualize and are we able to clearly access or do any kind of calculations for the load, so that we have clear picture of that, and we know that all the stresses, all the failure criteria, whatever we are using, it depends on the load. So, we need to know that load precisely, so that we have clarity on the parts dimensions and we can select the parts accordingly. So, in this case, if you take this example, pin clevis connection. So, yes, these are the external loads what we have. So, this is what we see, but there are many parts here, the pin is here. So, when we are applying this load, the tensions, tensile load when we are giving, how is it traveling? So, yes, I think if we can see through and if we are able to visualize, but we realize that okay, it will be on these parts. That's how it will be coming, and on the pin, this is where it will be applying the load, right. So, if we are aware of this, we also understand that the pin will have a lot of shear load and it may fail because of the shear. So, we have to visualize and in our design how is it traveling in our components, in our modules, in our assemblies. So, general rule of thumb, and of course, it's coming from the experienced designers who are building machines, and some are very intuitive. Short, yes, it has to be short, because otherwise if it's long, then we have many components will come on the way and we have to check their safety, their failure. But if it's a short, yes, it's mitigated easily, and so that's obvious. Direct, yes, if it's directly going to the frame or to the part, that's also good. In a line or in a plane, depending on the case. If there is a lot of offset, then there will be different kind of loading. So, one load can create a bending load, it can also create torsional load. So, if there is offset, so it's very good if it's along a line, if not in a plane. Symmetric, yes, you distribute. So, we know that like carrying a load, if it's a symmetric, then it's very good. If it's a asymmetric load, then we have to do a lot of arrangements to mitigate that problem. Non-redundant or elastic. If it can be locally close, that's even good. It may not transfer to the other components. And of course, if it's easily analyzed, then we should be able to dimension the parts accurately. We know exactly which part is going to fail, or if it's a large load, then which part has to be designed for that particular load. So, if we know for sure that what kind of loading is there, then it's always better, and we can always calculate in the beginning itself. So, some designs here. So, for instance, wall mounted soap dispensers we have. So, there are two designs, pull and push type, and mounted against the wall. Which one is preferred? So, one is, so in case of pull type, you are applying a load. So, the box may be anchored through some screws or bolts. So, indirect load path includes wall anchors, right. You have the wall anchor, so it's anchored to the wall, and all the time you are just pulling it, and suppose sometimes it's not dispensing anything, empty, and yeah, somebody can just get angry and just pull it with a very large force, and okay, everything will be on the floor. On the other hand, if you have the push type, it's a direct. You are just pushing against the wall. So, it's a direct, the anchor, everything not coming into the picture. They are not taking any load, this load, the external load, they are not part of it. The anchor, the anchor has only one role, is just provide the support so that it stays there, but it's not sharing any load because of this. So, the directly to the wall surface, and of course, this is the better design. In many examples, in many applications, we use helical gears, and what we realize that they develop thrust. So, and this thrust will pass to the bearings through the shafts. So, now it's taking very long route, right. So, if we take the load path, then we have to see the entire assembly and see how it's going, and many times we make a provision for that. We try to put some bearings which can take this thrust. So, helical gears, they develop thrust which is opposed by the assembly, and usually we use thrust bearings for that. So, it's taking longer path. How to mitigate that? So, there is another kind of design which is called herringbone helical gears. So, opposing gears, and what we see here is it's getting mitigated locally. So, thrust load is closed within the herringbone gears. So, one set develops it, other set cancels it. So, it just cancelled out locally. So, locally closed load paths are preferred if it's possible. So, in this case locally closed load path. So, the design eliminates axial thrust and it eliminates the thrust bearing also. So, it is a saving again if we try to localize the load path. One very good example is even this bicycles, the brakes, how we close it. So, we do not push or pull the brakes, but we simply squeeze it, and the load path stays local within the hand. So, even if we are cycling at a very high speed and if we have to suddenly brake, it may not create a problem. And what we also realize that yes, if we are cycling with one hand and then brake, then other dynamics will come into the picture and the person may fall, but he or she may not fall because of this. So, to prevent any kind of falling imbalance during braking, what we always do is we apply both the brakes together and both hands on the handle, and we use the symmetry. So, when we brake, so the inertia force is there, the cycle is getting a stop, but then our inertia is there and we try to fall forward. But if you are using one hand only, then it is getting transferred to the handle and then it can easily bend and person can fall. So, it is very dangerous, but if you use both hands, it is getting distributed, symmetric. So, I think it is many times obvious, but are we using these philosophies or these rules, what we call it, in the design or in our machines? So, again here the load path is locally closed, pulling rather than squeezing a bicycle handbrake, would be perilous, because if you try to just push or pull with for instance, you assume that this brake wire is just hanging loose and then you have to apply the brake just by pulling it, it will be disastrous. So, one of the way to visualize the load path is to look at the force flow. So, if we are able to visualize that, then what we see, if we plot force as fluid flowing through the structure and the joints, what we see that these fluid lines, they converge, diverge, even change directions, and that will help us to visualize, like if there is any kind of stress concentration and the nature of the forces, the loads, and then we do the calculation accordingly. So, there should be some design goals. So, equal distribution of flow lines throughout, the shortest and the most direct load path, minimize the number of times flow lines converge and diverge, avoid concentration of flow lines or mitigate possible failures, gentle rather than abrupt changes in directions, and again avoid bunching around corners. So, similar philosophy, and I think we can easily relate to the stresses. So, if we are able to visualize that, we will be able to see how the load path is there and whether it has to be addressed properly if they are not meeting the guidelines, or we may have to be aware of the consequences if we are deviating from these simple principles. So, this is one example, the gear teeth. So, detailed force flow lines in a gear set and even the keyed shaft and tension compressions here. So, you can see it is all converging. So, here contact, so compression. So, all lines now converging here, then again then at the gear tooth you have shear load, here compression, and again there is a tension, again is coming to the keys here. So, shear load and then passing to the shaft. So, if we are able to visualize these force flow lines, we are able to see the load path, then we will be able to also address the problem associated with it. And if we see any kind of deviations, we should be then aware of and then take corrective action to resolve those problems. The another rule is triangulate parts and a structure to make them stiffer. So, we talk about rigid bodies and we talk about the exact constraint design, assuming that they are perfectly rigid, but we are aware that everything has a limited stiffness. So, depending on the requirement, if we are looking for rigidity, higher stiffness, then how we should design it, and one of the way is the triangulation of the parts and the structures. So, many times when we are talking about the structure and the structural elements, which is important to design even machine base or which is supporting the moving parts, we may have to use triangulation, and this is important, particularly important when you want to need to have high rigidity, high stiffness, and want it to be strong. So, very good example is like for instance these swinging gates made of woods, so the wooden planks. What we realize that these kind of structures, so there are hinge joints here, maybe we have many parallel things. What we realize that when we have these kind of structures, and so sometimes we feel is fine, and we depend a lot on the joints. So, we have to make very good joints, but what happens because of the usage, because of its own weight, these joints will slowly wear out or give up, and then there will be sagging. And since it is a parallel structure, it does not provide any constraint. So, what to do? And what you see here is a parallel structure. So, And we know that if we just triangulate any triangle, if we take, if we three members, if we simply connect through some kind of pins, even with the pin we place, we don't have to weld it, we don't have to make them rigid. The joints don't take any load here. It's all so. If we take this kind of construction with the only pins, it's not going anywhere. So it's such a good design. In 3D it will be different. Yes, it's called tetrahedron. So, but the in any plane is the triangle, and one triangle you put, you will solve all the problem. So in this case, this is the parallel structure you have. If you don't have the triangle in place, no matter how many you put, actually in a way it will be worse, because you are simply adding weight without constraining that movement. There is no way to constrain this movement, there is always a degree of freedom. So that will not solve. Yes, many times we put this kind of things, angles, that is one of the way. But what do you realize, that if you just put a tensile member here, tensile cable, this will work, because what happens in this case is trying to just sag like this. So if you have this tensile member, it has to extend, right? So if you just lock it, this will not happen. So putting diagonal, connecting those diagonals, and if we do the free body diagram, we realize that there will be only tension. So even a cable is good enough, good solutions. And in that case, moment we have that, what we realize that we may not have to worry about these joints anymore. So same thing applies to any machine frame. If we have that kind of thing in place, we don't have to weld or make those joints very rigid. But if that single element is not there, if this diagonal element is not there, even though if we make these joints very stiff, after some time it will give up and we will have a problem. So if we understand these rules, how to get the rigidity, I think it's very easy to eliminate and rectify the problem. So structure without triangulating members, they have to rely on rigidity of the connecting joints. That's very important. So, but if it's triangulated, this is not required anymore. So it's very important to understand this part. At the same time, suppose if we want to just use a compressive member, it's just other way around. So because this length, now if you take any cross section, then there will be compressive load coming. So it will also avoid for the sagging. So this will not be possible in this case. So triangulation is a very good solution, and depending on the nature of force coming on the member, if it's just tensile, we can usually use any kind of flexible steel cables and resolve it. So we can see these days in many of the furniture designs. Another way to resolve this kind of problem is to use shear plane or shear waves. So this also provides that triangulation, because they cannot deform diagonally. So it provides that constraint. So this constraint is provided. But the idea is they should be part of it. It should not be simply placed at the back of the rack. So if it's just placed at the back of the rack, it will not constrain, and therefore then it's not part of that structure. So, in order it to work efficiently, it should be part of this frame and properly secured. So, whenever we receive these kind of bookcases or any kind of furniture, modular design these days, we should make sure that they are properly secured, so that that triangulation we get, and the bookshelf or any kind of furniture, it should not get shaky. Again, here what it says is, so side to side will not collapse, because this will prevent, it will get, so this will not happen. But what will happen to this corner to curtain? So, that still has to be solved. So, corner to corner movement. So, diagonal. So, we will see some examples later how to resolve that issue. So, again there are some box design, and many times we need the opening, and at the same time we also want to have a stiffer structures. So, if it is a closed box, definitely it is a stiffer, but the opening is important, and that is why one of the way is to get the stiffening flange like this, and this will provide the required stiffness, the triangulation required, and we will get a stiff box with the opening. But we also realize we provide ribs in many of the designs, to provide a proper support with the structure, with the base. So, thin ribs and ribs. So, it again adds rigidity to the structure. In 3D is a tetrahedron structure, so you can simply connect and you can see it's now tetrahedron. So, this is very stiff structure, and again here you do not have to worry about the individual joints, but they have to be simply placed as long as they are part of the triangle. So, any way you check, they are triangles. So, if the triangulation is done, it will provide very high rigidity and very high stiffness. So, in case of three-dimensional structures, we go for tetrahedron structures. But be aware, triangulation does not mean it will solve all the purpose, right? It will definitely stiffen the structure, but it does not mean always stronger and robust. Why? Because when we stiffen the structure, it transfers the loads to a different place, right, and that may be weak, or susceptible to all kind of fracture, failure, corrosion, right. So, we have to be always aware that when we are providing that extra stiffness, extra rigidity, how the load is getting transferred. So, again we have to be aware of the load path, and we have to look at it together, that if it is getting transferred from one place to another, right, and the stiffness is provided at one point, how is getting mitigated to another place, or whether it is affecting the part elsewhere. So, we have to be aware of the consequences again. So, we will continue in the next lecture about this. So, why to avoid bending stresses, why to prefer tension and compression. So, we will continue in the next lecture. Thank you.